part B.3, Smoothness Rule. All right, so this part is very theoretical, very abstract, not very easy to understand. But first, let me explain why I need to talk about this topic. We derived the formula from the example count binary digits. We solved that problem. But after we find the solution, we want to summarize a little bit. Is there some general rule we can get from there? Because in future, we may have many other similar problems. When we have the similar situation, can we just get our result immediately without going through all those difficult steps, mathematical induction, step-by-step proof, very complicated? Can we derive some theory or theorem that we can apply on our problem directly to get the result? So that's what we need to do in this video. All right. From our solution, so what we have is like this. First, when we try the special case, n is power of 2, we can easily show the formula is correct. Second, when we move to the general case, it is very hard. We need to do a lot of difficult work to verify it, guess and verify. That step, very, very complicated. I do not know how many of you can follow my mathematical deduction part of the previous video. I hope all you can, but I believe there are quite some of you couldn't follow the details. Try your best to follow. All right, so here we try to avoid that part. So in the future, when we have the similar situation, we want to apply some theorem. Definitely the theorem must be proved. As soon as we prove that theorem, then later we just use it. All right, so the situation, the theorem, we call it Smoothness Rule. That's in our textbook location, this page, Appendix B. Definitely, I do not try to prove it. So if you are interested, you can read the proof. But we are not required. We just understand the theorem and we can use it when we need it. The situation is this. We need a general result to address the similar situation. So here I do not repeat the same situation. The situation I'm talking about is here. All right. Smoothness rule. First, let me give you the detail of this theorem. It is not easy to understand. I need to use this slide and next slide to explain the meaning. Let T of n be an eventually non-decreasing function. First, we define a special function called eventually non-decreasing function. We will define it in the next slide, but you can guess its meaning is obvious. Non-decreasing, you know the meaning, right? The function non-decreasing. It can be increasing or it can be flat, or sometimes flat, sometimes increasing, but non-decreasing. Eventually, only thing is this eventually. We know we don't care the beginning part. The beginning part you do decreasing is fine, but eventually after some point, after you hit some point, then never decreasing. So that's the eventually decreasing. That's the meaning. then and f of n, little f of n, be a smooth function. Now, what's the meaning of the smooth function? I explain in the next slide. Its meaning also very complicated. Smooth function, new meaning. Okay. If t of n belongs to big theta of f of n for values of n that are power of b. See, power of b, power of 2. Okay, so that's the same situation. Okay, where b greater or equal to 2. So not necessarily 2, could be, other b numbers. If you can prove that, then t of n also belongs to, because look at the situation. The t of n belongs to this only true for power of b. But now you can generalize to this is true for n greater or equal to n0, right? Why? Here I use this greater or equal to 0, because eventually, look at this. Eventually means you have some n0. After you pass the n0, then you have that property. So here we have that. For n greater or equal to 0. All right. That's the meaning of the smoothness rule. But I need to explain these two concepts. Then, after you understand that, you can apply this theorem. But the first one is easy, but the second one a little hard. Let's look at the first one, eventually non-decreasing function. That's pretty straightforward. F of n non-negative function could be, increasing, decreasing, right? Called eventually non-decreasing if there exists non-negative integer, this n0. That corresponds to the eventually part. So you need to find that special n0. After you pass that line, vertical line, then you have the nice property. Before that line, you do not have the good property, but you can skip that part. Okay, so that part I use overhead to explain before, right? So sometimes we need to pay overhead on that, messy part. Not good part. Okay, the messy part. All right. So that f of n is non-decreasing in this interval. Non-decreasing, if we use math formula, then we can use expression like this. When n2 greater than n1, definitely both greater or equal to n0, the function values also follow the same trend. Okay? So when you move the n variable to the right, then the function value going up, or at least equal or up. All right. So that's the first concept. The second concept. Before we move to second concept, let me show you one simple example. So that's our function, right? Log base 2 of n. So you can see log base 2 of n, definitely no problem, is eventually non-decreasing, right? I may draw another function and ask you if it's eventually non-decreasing, like parabola, right? Things like that. You have some portion decreasing. This portion decreasing. But after this line, central axis, now it's increasing. That parabola. All right. Smooth functions. The definition: if f of n be let be a non-negative function defined set of natural numbers, 0, 1, 2, 3 natural numbers. f of n is called smooth. All right, so this word, smooth, if it is eventually non-decreasing. The first part, easy. Second part, this is the critical condition. F of 2n, so you double the size of the problem. 2n, f of 2n, it still belongs to the same asymptotic class of the functions, big theta of f of n. Okay, yeah. So that is the critical property of this function. Okay, if we use our current function to check it, okay, so we double the size. When we double, we take that one out. So you take that one out, it does not impact much. We know the minor term, right? Yeah, because this less than or equal to, we can prove the big theta, right? So remember upper bound, lower bound. Upper bound, can we use 2? From upper bound, we can use 2, right? Yeah. Lower bound, we just use 1, okay? We just use 1. Okay, yeah. So you can see this is also in the big theta of, big theta of log, yeah. We can remove that floor function, okay? So we don't need a floor function, yeah. So we can, even write log, sometimes log basis is not important, right? So we can simplify to this, yeah. The base is not important, yeah. All right, yeah. So you can see, satisfy that condition. So based on the definition, this function is smooth. Yeah. But the last thing I want to mention, the word we use smooth here is different from the smooth function in calculus. So do not get confused in calculus. Okay, yeah. Do not confuse in calculus. Yeah. Calculus smooth usually related to differentiable, if the function is differentiable. But here, our function is not differentiable, right? Yeah. So the floor function, not differentiable. So you cannot say in calculus it is not a smooth function. Yeah. But do not mess up. Yeah. Do not get confused. We do not mean the calculus smooth. We mean the computer science algorithm smooth. Yeah. All right, so that's the B.3. Yeah.